Let's get started. So again, my name's James, and we're here with Dr. Ben and I, Alex over here, and a couple of guys joining us today. Max, say what up. Tori's over here. So we're happy to be here. Let's review with, well, this is our schedule for today. So we're going to review a little bit of what we did last time. We're going to talk about seismic design. You guys have associated the words earthquake and seismic, right? When I say seismic, I'm talking about earthquake. And then we're going to introduce the project that you guys will be doing and demoing the structure. So just like last time, have notes out, take notes. I'll ask you a couple questions. And there's even some fun surprises in there. So be alert and aware.
And James, I commended them on how well they were focusing and taking notes last time.
Beautiful.
And I also let them know that I noticed a couple of them were taking notes, and that if they're all stuck or don't understand and are feeling frustrated, that we're all friends here, right? This is a good environment, and your question is probably something that somebody else would like to ask as well. So if you feel stuck, raise your hand. You can always say, could you repeat what you just said? Or you can say, I had no clue about what you were just telling us, whichever you're comfortable with. So that's a nice way to do it. Could you repeat that, please? Instead of saying, sorry, I have no clue. A little easier to do that.
Perfect.
Bye, Christopher. Yeah, all right.
Who's Christopher?
Christopher is my buddy over there.
Christopher. Okay. I think I have some of the names down. Kevin over here. Is there a Devin?
Yeah.
Yeah, Devin. Nicole's over here. Evan and Ronak, I met you guys earlier, and I know Christopher too. I might remember some of those other names too if you tell me when I ask you the question. All right, let's talk about what we learned last time. So here's our engineer dude. This time he's got a suit on. Who remembers what this is about? Capacity and demand. Good. Okay. Another way to say this, by the way, is just capacity needs to be greater than demand. Okay, it's the same thing as saying C over D greater than 1. You could also just say capacity greater than demand. Who can give me an example of capacity and demand? Yeah, Christopher.
Sitting on the chair, my weight has to be less than the demand that the chair can hold.
Close. Your weight is the demand, and the capacity is how much the chair can hold. Okay?
Lollipop.
Lollipop? Oh, we're not there at the lollipops yet. We'll get there. You're ruining the surprise. Okay? And then we're considering different types of loads. Okay? As engineers, structural engineers, we think of each load on the structure differently, and it has a different name. All right? Speaking of quotes, maybe this is the definition of a structure. We talked about that. We talked about earthquakes too. We said this is bad. That's also bad. This is bad. This is very bad. Of course, that is also bad. That's not supposed to happen. These things are not supposed to happen. They're not supposed to break. And anything that's not supposed to break needs a structural engineer. That's what we talked about last time. Fair enough? Good review? Does that ring any bells in there? Okay, great. So, seismic design. We're going to talk about the difference between the word static and dynamic and what that means for our structure. Okay? So static means not moving. In a static case on our structure, we have different vertical forces. We have the self-weight. That's just the weight of the actual building. That's a dead load. We have people or furniture. Those are live loads. Or maybe rain and snow. Also a live load. What's the difference between a dead load and a live load? Here's your surprise, by the way. Answer a question, I'll throw a lollipop at you. If you catch it, you can eat it. What's the difference?
A dead load is something that can't be moved, and a live load is something that changes.
Good, awesome. Very good. Great. Dynamic means moving. In a dynamic case, our structure still has all the same vertical forces, but now it also has horizontal forces, like wind or seismic. What is this load type? Someone raise their hand. What's your name?
Nick.
Nick?
It's a dynamic.
That's not it. Not Christopher. What's your name?
Paul.
Paul.
Environmental.
Environmental. Good. So wind loads, seismic loads, these are environmental loads. They're actually a type of live load because they change. But if we're talking about them being caused by some external factor, we'll call them environmental loads. Easy enough. Static and dynamic. Okay? All right. Load path. So in a static case and the dynamic case, as structural engineers, we're focused on something called load path. And the load path is the way forces move through the structure and into the ground. So we talked about capacity and demand and how the capacity of each component needs to be greater than the demand for that component. And the way you go about figuring out what the demand is you follow the load path. Okay? Looks something like this. So all the weight is going from the top down into the ground, and there's not a lot going on here. Okay, this, for example, this is we call this a beam. We call these columns. This beam is going to bend a little bit. It's transmitting something called moments, which are a type of force, over to these columns, and that's going down to the ground. Okay, this is a static case because the structure isn't moving. We have a dynamic case as well. We still have the dead and live load. Here are our wind or our seismic loads, but now, when we follow our load path, we see that the demand, well actually, I forgot about this. Is the demand now larger or smaller in this case? Someone raise your hand. I already know your name, so I'm looking for someone whose name I don't know. Help me out. Oh, okay, what's your name?
Cole?
Cole.
I'm so confused.
All right, is the demand now larger or smaller?
Larger?
Larger, good.
Cole. Can't eat
I
it
hit
now.
too hard. Should have gone underhanded. Okay, so if the demand increases in our dynamic case, then in order to satisfy the capacity being larger than the demand, we need something to increase the capacity. Does that make sense? You don't even have to know a lot to understand that if the demand is going to increase, then we somehow need to increase the capacity. Right? Another example we used to talk about capacity and demand was the capacity of this room in terms of people. Right? We have maybe 40 people in here right now, and the capacity is maybe 60, so we're good. What if we decided we wanted to have a class with 75 people in here? Well, we would need to find a room that has larger capacity to fit that amount of people. Does that make sense? Same idea here. If our structure is experiencing a dynamic case, then the demand is going to be increased for these components, and we have to deal with that. The way we deal with that is with something called an LFRS, which is lateral force resisting system, and that'll show up again, so I'll repeat myself on that. How are we going to increase that capacity? Well, before we talk about that specifically, let's talk about why we need to increase the capacity and why we need a lateral force resisting system. So we're going to talk about stability. So here's this little basic structure, okay? These little circles, they're hinges. Think of them like a chain link, right? Like it can just bend around like this. Can you imagine that? Okay. What's going to happen? Okay, I'll start calling people that I know. Kevin, what's going to happen?
The load is going to tilt to the right.
Okay, yeah. What's going to happen to the structure? If these things are just hinges like that, what's going to happen? I'm going to move. White jacket. What's your name?
Jay,
Jay. All right.
it's gonna collapse.
It's going to collapse. That's the answer I was looking for.
My hand was up.
Like this. This is not stable. Okay. Do you guys want to see it again? Not stable. Okay. What can we do to make it stable? Any ideas or not? Good. You're imagining an X? Is that what you're imagining? Yeah. Ronak says we can put an X. So two other members that maybe look just like this going that way. Would that work? You guys think? Yeah. Okay. It would. So this is why we need a lateral force resisting system, and there's three main types. So, just like he said, we can make an X. Okay? Are you guys drawing this? I'll go slow here if you want to draw these out. So So there's 3 of them just like this with hinges. They're going to fall over. So this one, we give it an X. With this one, we fix this joint, right? You can kind of think of this as if you weren't going to add another piece, you could also maybe glue that really well, okay? But the idea is you're now fixing that. So this angle here is not going to move. It's not going to change. The angle is going to stay constant, more or less. It's all about the connection here, all right? These all have names. I'm about to tell you what they are. The last thing we could do is simply this, right? The whole thing is a wall, and it's not going to tip over. Make sense? Okay, they all have names. This is called the braced frame. The X is called the braced frame. This one is called a moment frame. You can think of it as a fixed joint frame. Those joints have to be fixed. So we call it a moment frame. And a shear wall. Okay? So now we're going to spend some time talking about these specifically. There's pros and cons. They all act differently. So we're going to talk about that. But I want to know, in terms of stiffness, how would you guys rank these? From the most stiff to the least stiff.
The most stiff would probably be like the shear wall, and
Okay.
then the brace frame, and then the moment frame.
Bingo. Good job. What's your name?
Eric,
Eric.
I can learn stuff.
Okay. So here's some examples of brace frames. All right? They come in different configurations. So here's an X. This is called chevron bracing. These are called eccentrically braced frames. You don't have to know that. You don't have to know those names. But the point is, they can come in different configurations. I have it right. Is that called eccentrically braced frames?
Yeah.
Okay. But it's important to realize they go all the way up. Notice that they're going all the way up, but they come in different configurations. But they don't have to be in every bay. So a bay is in the space between these columns. So these all have 3 bays. Does that make sense? 3 bays. They don't have to be in every bay. If in this like in this case is if you just made 1 bay a brace frame, then the whole thing would be then you would have a lateral force resisting system for that whole section. Does that make sense? So you don't have to put X's everywhere to get a brace frame. There's pros and cons. So pros here, there's moderate stiffness, like we said, in the middle. There's not a lot. There's not a little material. There's not a lot of material, so it's a good amount of material. The design is pretty simple, but there's some bad things too. For example, if we wanted windows here, we couldn't have a window with a brace. Maybe you could, but whoever's office had the big brace in front of it, they'd be a little bummed out. So that's one con. The other thing is there's something called ductility. I'm not going to talk about that a lot, but in general, it's the idea that your structure is not supposed to move, but it does need to move a little bit. If it's too stiff, that could be a bad thing. And with braced frames, there's sometimes an issue of ductility. It's sometimes harder to get the exact ductility that you want. Not always. It just takes a little more focused design. Pros and cons here. Okay, moment frames. So with moment frames, it's really important to understand the connection. So if you don't see a brace and you don't see your shear wall, that doesn't mean it's a moment frame. A moment frame has very specific connections here. Can you guys visualize this, by the way? I didn't even think of that. This is a column going up like this. These are beams like there and there. Can you guys visualize that? Okay. And
Do
these
you know what kind of material that's made out of? Those types?
Steel.
Steel.
Awesome. Good job. These are steel moment frames. The connections are very important here because they have to stay rigid. So when the thing moves, that angle is still supposed to be 90 degrees more or less. Unlike that structure that would just tip over. That structure that tipped over didn't have a wall. It didn't have a brace, but that doesn't mean it's a moment frame. So here, just because there's no brace and no wall, that doesn't mean that this is a moment frame. A moment frame has very specific connections. There's pros and cons here. For example, we can get a lot of the windows that we want. We don't have anything in the way, and we could get. It's a little more flexible. So if we want that, it's easier to get the right flexibility if that's what you want. The cons, it's very complicated in terms of construction and design of those connections because it has to be like really precise. There's a lot of precision involved. I think there could also be more construction costs because the welding has to be really specific. So hiring welders is more expensive than if you have a braced frame that is connected with bolts. Anyway, so pros and cons here too. Let's talk about shear walls. Here's some examples here. One thing I want you guys to realize is, do you guys know what this stuff is sticking out of the top of that concrete? Rebar. Good. Rebar stands for reinforcement. It's steel that goes inside concrete to reinforce the concrete. Concrete is something that's called a brittle material. That means it doesn't take tension forces very well. Steel takes tension forces very well, so we reinforce the concrete by putting these cages of rebar. And you don't even have to understand all those technical terms, just to imagine that if you had all this concrete that had like a steel cage in it, it's probably going to be stronger. We can kind of just shrug and most people will kind of understand that, right? So shear walls look like this. They can also go in different configurations, and they also don't have to be in every bay. Just like you see here, you can kind of put shear walls in different spaces. And not every wall is a shear wall, right? If we look at this structure, at the end of the day, when this thing is all done being built, the structure's not going to look like this. There's going to be walls everywhere, right? Like this is not just going to be open inside into the building. It's going to be covered with a wall and maybe some doors on the outside, on the end. But that doesn't mean that everything that looks like a wall is a shear wall. So not every wall is a shear wall. They also have to be specifically designed to be a shear wall. They have to handle those lateral forces. Remember, lateral force resisting systems. Oh, I think I left that as structural. I should have changed it to lateral. Lateral force resisting systems. That's what we're talking about here. Okay. This one is masonry. Okay, moving on. Pros and cons here. If we need a lot of stiffness, these are pretty stiff. Like we said before when we ranked them. What was the name? Eric, yeah. Okay. High stiffness. The design difficulty is not as complicated as something like a moment frame when you have to be really precise. Of course, all these things take time. I don't want you to think that some of them are just like, okay, just shear wall, here we go. As structural engineers, there's still a lot of detailing going on here. We also can't put a window there. And there's a lot of material. So there's pros and cons to all these things. Some closing thoughts about all of them. For a moment frame, what we care about most is those connections. Those have to be very precise, very well defined. Again, just because it doesn't have a brace and it's not a wall doesn't make it a moment frame. For our brace frames, they're various configurations, and they don't need to be in every bay. Same thing for a shear wall. Not every wall is a shear wall. Not every wall is created equal. So, but all of them must go from the bottom to the top of the structure. Why do you think that is? What's your name?
Kane.
Kane?
Yeah.
Why do you think that all these lateral force resisting systems need to go from the top to the bottom?
Oh, from top to bottom?
Huh?
From top to bottom or from bottom?
From bottom to the top. I mean, they have to go the whole height. Why do you think that has to be?
Stronger foundation.
Okay. That's not quite the right answer, but I like the way you're thinking. Your name?
Aaron,
Aaron?
to give support to the whole structure, the whole building.
Okay. That's also true. Think about some of the things we've talked about before. There's a specific two-word answer that I'm looking for. Nicole?
Because if you skipped any places, it would snap at the weekends.
Okay, that's very true. And there's a specific reason about it. And we talked about it before. Two-word answer. First letter of the first word is L. Second letter, now we know who it is. Okay.
To reduce the load, or help the load path.
Load path. The answer is load path. Good job. Here you go. Is that your second one? Here's my analogy. I always like to think of analogies that aren't structural, like I did with the guys lifting weights and all that stuff. To help me understand structural engineering, sometimes I think of analogies that aren't really structural at all. So the one that I think of here is, think of a rain gutter. Okay, a rain gutter starts at the top of the building, and it goes all the way down. The pipes go all the way down and get the rain out, right? Think of force like rain. If you had a rain gutter that started on the top and then like went down, the pipe went down a level, all of a sudden the pipe just skipped and then started again, right? What would happen to all that rain? It couldn't go down to the next pipe. It would just kind of spray out, right? So think of load path the same way. It has to be continuous. The idea is to get the force. Remember, the lateral force resisting system is what we use to get the force out of the structure into the ground. So it has to be continuous. So for all these lateral force resisting systems, it has to be the whole height of the structure. Okay?
Okay, don't. Okay, go ahead.
Yeah?
Finish your statement and then I have something to add.
Beautiful. And the last thing I'll say is there's nothing that's magic. Okay? They all have pros and cons, like we talked about. And as structural engineers, we choose the right one for the right situation. So I don't want you to think coming out of this, oh, this one he listed more pros, less cons, so that must be the better one.
So all I wanted to mention was, especially if you look at this picture of the shear walls, why do you think they're placed where they are right there? Do you want to pick a person? He's already got one. Does anyone want to answer besides, what was your name again?
Nick.
Nick. What about here?
Those points are might be where they tilt the building.
Where the building tilts. Not quite what I'm getting at. Anyone else have another idea? Go. Oh, you want to?
Might be the weakest ones.
Might be the weakest points. Okay. These are all good things. Yes.
They're spaced out enough where a force could be applied anywhere.
Okay, so you guys are all thinking very well about load path, because we just talked about load path, and all of these, like, this might be a weaker section. What type of loads are these lateral force resisting systems trying to withstand? What kind of loads did we talk about? We talked about dead loads and live loads. What kind of loads is this one trying to withstand? Do you have any candy you want to throw out to anyone? Yes.
Environmental.
Environmental, right? So lateral loads like earthquakes and wind, right? So what do we know about wind and earthquakes? Yes.
They come from all places.
That's right. So when you guys are sitting here and an earthquake strikes us, or a big type rainstorm coming in, right, with a lot of wind, we don't necessarily know which direction that earthquake is going to hit us, right? Is it going to come and shake our building this way, or is it going to come and shake our building this way, right? And so that's why these systems are placed in different configurations, because we don't know what the demand is going to be, what the earthquake load is going to be. Does that make sense? Okay.
Good. Thank you. Great. So we did static and dynamic. Dynamic requires a different load path, and in order to handle that different load path and that greater demand, we have lateral force resisting systems. That word is so hard to say, I have to slow down every time I say it. Okay. So, do you think that the LFRS is going to completely stop the building from shaking? No, it's not going to stop the building totally from shaking. If we have a building, it's still going to shake a little bit. Want to see it again? I'm really happy about all my animations, just so you know. So because it's not totally going to stop, as engineers, we have to understand how it's going to shake. Our LFRS is not going to stop it from shaking, so we have to understand how it's going to shake. We have to come up with a mathematical way of describing this motion. And the best way to do that is to start with a very simple model, okay? So that simple model we're going to use is called a lollipop model, all right? So basically, this is a way of thinking about our structure as something really simple that looks like a lollipop. That's why I'm throwing out lollipops today. This simplified model works by maintaining two important properties, mass and stiffness. We talked about those for a second when we said you guys kind of guess what different LFRS is going to have more or less stiffness. Those are two really important properties when it comes to understanding how things shake, is their mass and their stiffness. So if we can make some model like this that has the same stiffness as this guy and the same mass, then it's a really good way of it's a really good simplified model of understanding how things shake. So we represent the mass of the structure by lumping it at the top of the lollipop. So a bigger lollipop will need more mass. Simple enough, right? To represent mass, we use the letter M. It's in units of kilograms for the metric system. So more mass means that there's more matter as well as more weight. To represent the property of stiffness, it's represented by the height of the lollipop. So a shorter lollipop would be stiffer, and a taller lollipop would be less stiff. We can imagine that, right? If I push on this, it's going to move a little bit. This guy's going to move more or less. If I push with the same force, it's going to move more. This guy, the most, right? He's the most stiff. He's the least stiff, right? So that's how we represent the stiffness and the mass of our structure. Stiffness being the height, mass being the size of the lollipop at the top. The units are in newtons per meter in the metric system. And to understand it briefly, more stiffness means that you have to push harder to move the structure, right? And I wanted to let you guys know, stiffness isn't something that you guys, maybe, have you guys talked about like Hooke's law? They talked about that, like F equals kx. You guys have seen that equation? Okay, good. So you know what stiffness is. But there's a very, to calculate the stiffness of a structure that looks like, I don't have to show you, but you know the picture I had up there before. To calculate the stiffness of that structure requires very specific understanding that we're not going to require you guys to know. So we'll give you a simple formula to calculate the stiffness of your structures, just so you know. I don't want you to get afraid of that idea. Okay, so we're building this model to represent our structure because we know that even if it has an LFRS, it's still going to shake, and we have to understand how it's going to shake. So we've made our model, and we've kept two properties consistent, stiffness and mass. Now, we're going to talk about something called free vibration. So free vibration is what happens if you just flick the lollipop. So what happens if I flick this lollipop? Christopher?
It's going to like go back and forth.
Yeah, good. Forever?
No, it'll stop eventually.
It'll stop now. I'm just making sure there hasn't been people I've been calling on more than others. I want to make sure I'm seeing all your hands being raised. If you're on the ends, I might not see you, so you get my attention. Okay, good. So I'm going to flick the lollipop. Shakes back and forth. This is slow motion, and eventually it stops. Did you read my slide? Because back and forth, eventually stopping. That's it.
Yeah, I did.
Oh, okay. You got the email?
Yeah.
Okay. So, understanding this motion, free vibration. If we record the amount of time it takes for the lollipop to go back and forth, it will be the same every time. This tendency is very important when understanding how things vibrate. Okay? The idea is that when we shake it, the amount of time it gets back to this spot is going to be the same. When I flick the lollipop, it's going to go this way and it's going to come back. The amount of time it takes for it to get back to the other side is going to be the same every time. So we define two important properties. Natural frequency is the amount of times it shakes back and forth in 1 second. Okay, so we pull it back, we flick it. How many times does it get back to this side in 1 second? That's the natural frequency. Natural period is the amount of time it takes to shake back and forth one time. Okay, so we let it go, and it comes back. How much time elapsed? That's called the natural period. It's these things are defined the tendency that a structure has to vibrate. And it turns out that these two properties can be predicted based on the properties of mass and stiffness. You guys can probably imagine that, right? The taller lollipop, if I flicked it, do you think that it would go back faster or slower than a shorter lollipop? Slower or faster?
Faster.
Slower.
Okay.
Most people are saying slower. You'll visualize that with something later if it hasn't made sense to you yet. Okay? So here's our equation for natural frequency. 1 over 2 pi times the square root of stiffness over mass. The units are in cycles per second, also known as hertz. Love hertz. Hertz. Okay. Cycles per second is called hertz. The equation for natural period is just the inverse of natural frequency. Okay? Or we can solve it with this equation. As you can see, it's just the inverse. Flip the 2 pi over, put the m and the k. This will be in units of seconds. Hopefully you guys realize these are just two ways of talking about the same thing. Right? If something is shaking, I can talk about how many times it shakes per second, or I could say how long it takes to shake for one cycle. Okay? So let's do a quick calculation. I've given you the stiffness. I've given you the mass. Here's the equation. So get your calculators out.
Ouch. Dang it.
Here's your calculator.
You got it.
Okay, good.
2.78.
Really? It's close. Do you have an answer? I want to give everyone else a little more time. Raise your hand if you have an answer. I just wanted to add their answer, so you're right. Who has an answer? What'd you get? What's your name? Michelle, what'd you get? 3.18? Who else got 3.18? You are correct. 3.183 cycles per second. So I would have liked it if you guys told me the units. As engineers, units are important. Don't just say the number. The units are cycles per second or hertz. 3.183 hertz. What does this mean? Someone tell me, what does this number mean about this structure? Let me out. Oh, what's your name? Hannah? Okay. What does this number mean?
It means that it will, like in 1 second, it will touch your stocking for
Okay, good. Yeah, 3.183 cycles per second. Exactly. What's that? Oh my God. Oh, it was a little short, my bad. Okay, now let's calculate this. So, natural period. Let's calculate the natural period of the structure. Ready, go. You're already on top. You don't have to use a long equation, by the way. Do you remember this? Alright, Ronak. Everyone get 0.314?
I have no idea how to do that.
Minutes? Seconds. Seconds per cycle, but you can just say
I
seconds,
think I
okay?
messed up somewhere.
0.314 seconds. You can say, you don't have to say seconds per cycle. The natural period of this lollipop is 0.314 seconds, okay? So, when I flick the lollipop, it'll vibrate at 3.183 cycles per second. In other words, each cycle takes 0.314 seconds. Does that make sense? Two ways of thinking about the same thing. Man, look at that. Let's review. Okay? Some chance to get some more lollipops. If you haven't had a lollipop yet, chance to get a lollipop. Okay, so we talked about load path. Someone tell me why load path is important and what it is. Kevin?
Load path is the way forces move through the structure and into the ground. There are two types of load path. There's a static and dynamic.
Good. What's the difference between the two?
Static is non-moving and only vertical, while dynamic is moving and vertical and horizontal.
Good. Yeah. That was low. My bad. So the one thing I'll say, and my slide might have been a little confusing. There's still a horizontal demand, even just from dead load. The forces still have to go sideways and then down through the column. The idea is it's just much less than in the dynamic case when there's this horizontal load. Anything else about load path? Why is it important? The next little picture might actually help answer that. So we talked about these. What is LFRS? In half.
Lateral max.
Max, I like your shirt.
Thanks. Lateral force resisting system.
Lateral force resisting system. And what does it do?
It stops the structure from moving by earthquake or wind, or at least reduces, not
Yeah.
completely stops.
Or the really easy answer is a lateral force resisting system resists lateral forces.
Yeah.
Someone say no, you? No? Okay. What are these three types? In the gray shirt. What's your name?
Brian. There's brace frame, moment frame, and shear wall.
Okay. And which one's this?
Brace frame,
Good.
a moment frame, and a shear wall.
Oh, there's your moment frame. Heads up. Coming in hot. Nice catch. Okay. What about some pros and cons for each of these? The doctor?
Okay, so for brace frames, the pros are moderate stiffness, moderate material amount, and cons are loses window space, and it could be too stiff.
Okay, good. And what are some important? What are something important about it? Or there's a couple of other notes I said about it. I want to see if you have those too about brace frame. Are they always in the same shape?
Oh wait,
I'll give it to you. I was looking for various configurations. Sorry, that was not Kevin. I didn't even ask a question. He answered it, but what were you going to say?
There's the chevron.
Good.
And then there's the eccentric, and then you have the normal.
Yeah.
Very good.
Awesome. Very good.
You can get
Very good. It can be, and it can even be more specific from there, but great work. Okay, let's talk about shear walls. Someone just tell me something that you think is important about shear walls. In the red.
They're really stiff, but they need a lot of material.
Really stiff, use a lot of material. Good. Okay.
They're good against environmental loads.
I'll give that to you, but these are all supposed to be good. But I have extra, so. All right. Let's talk about moment frames. Good. I don't think I've heard from you yet. What's your name?
Dylan.
Dylan.
With more window space.
Good. Yeah, windows. And the back of the light? More flexible. Also true. Oh, way off. Good catch. All right. I wanted to give you guys an opportunity. If there's anything while I was talking about these, were there anything you like
Expensive because
thought
I'm
of?
buggy.
You should probably mention this about base frames, smoke frames, shear wall.
I know.
Some are hard to construct in the field, and you guys will figure out when you guys are making your structures, depending on what you guys put on there. Some will be easier to make, and some are harder.
Yep.
Cool. All right. Lollipop model. Why do we have a lollipop model? Someone tell me.
It's a simplified model of a structure.
Good. And why do we need it? You can hold the thought. Let's see. I'll ask somebody else. Nicole, why do we need that simplified model?
Use it to mathematically calculate how the structure will move under a load.
Exactly. Yeah. The idea is we need to understand mathematically how the structure is going to shake, how it's going to vibrate. So we create a simple model in order to understand that, right? And we don't all. So this is that kind of where we start from, right? But we have systems that can computer programs where I could build something like this and be very specific and tell all the material properties and all the sizes of everything, and then it could tell me exactly how it's going to vibrate. But we always kind of start with a simplified model, and so we have a simplified way of understanding it. What are the important properties for the Lollipop model? Yeah.
The thing at the top, the bigger it is, the more mass it has.
Yeah. Okay. What else? What's the other? So that's mass. What's the other important property?
The longer it is, the more.
Yep, what's that word?
I asked you. You answered the first question, but someone else tell me. Tell me about how we talked about the stiffness of it. I didn't. Well, I'm not going to give it to you now. That happens. Well, there's still lots of opportunities to get to. Yeah. So we talked about the other property is stiffness. The shorter it is, the stiffer it is. The taller it is, the less stiff it is. Or you can say flexible. Stiffness is the opposite of flexible. So the taller it is, the more flexible it is. Okay, and if we know those two properties, what can we predict? Two things. Back here, wait, Nick?
I give to Cole.
Okay, and what is that called? Okay, the names are important. Back there in the blue.
The natural frequency is the amount of times it shakes in 1 second, and the natural period is the amount of time it takes to shake back and forth once.
Awesome.
What flavor is that?
Oh, that was right at you. Sorry.
Good reaction.
All right. So that's about it. Okay. So now we're going to do a demo. Demo is a word that is short for demonstration. It is also a word that is short for demolish. And both of those things will happen. Yeah, I'm going to put the mask on. This is Malix. The structure is named Malix because it was built by Corey.
Yeah.
It was built by Max and Alex, so it's called Malix. That was really important. He wanted me to say that. Does this have an LFRS that you can see?
Yes.
Yes? No?
Yes.
Who says there's an LFRS? Raise your hand if you say there is. Raise your hand if you say there isn't. Okay. For those of you that said there is one, what is it? What type of lateral force resisting system do you see? You don't see one, do you?
He sees one.
Oh, what is it?
What was the brace frame?
There's
Like not really a brace frame,
It is a frame.
It's just a frame.
A moment.
There is no LFRS here. There is no shear wall. There is no brace frame. There is no moment frame. Right? Moment frames have very specific connections. We haven't done anything to reinforce these connections. So if this thing does not have an LFRS, what do we expect to happen when we shake it? It's going to fall. Yeah.
So we're going to get into this project, but pay attention to this particular structure, okay? Because you guys will be starting by building this structure first, okay? And these guys built it. It's the first time they've ever used balsa wood to build a structure like this, and they'll tell you it's tough from the beginning. It's tough to get things aligned. If you look at it from this direction, kind of turns and symmetry is important and things like that. So just pay attention to the.
Make sure you cut, when you cut it, you can see if it's at an angle. Make sure that it's not at an angle.
And we'll give you some construction techniques next time when we come in, kind of a thing. But the first step you guys are going to do is reproduce this building, okay?
2% battery, but it's worth it.
Okay, so what is this case? What is this load case? Okay, is it moving? No, what is it called? Static. This is a static load case. You could call this a dead load. You might also call this a live. This mass at the top represents the dead load and the live load. So there could be people in here and furniture, which would be live loads. And this is representing all that. It's also representing all the weight of the walls that would be built on here. You guys can't tell, but it's very flimsy right now. So
I'm being careful.
I'm being really careful when I put this on.
Oh no, he's going to catch it. Right, James?
Yeah.
When these things fail, sometimes they fail very quickly, which is why we love slow-mo video. Phones that allow you to do more analysis. We'll talk about that. We're going to use that with a couple of our physics labs too. But
Someone send me the phone video. I want to see it fall.
Oh, you got a while ago. Yeah.
It's dissolving. I think it's in the mouth.
Yeah, the stick.
Yeah, the actual stuff.
Yeah, it's so gross. That's why this big rock can start coming off.
All right, so this earthquake record that we're about to, hold all the videos. This earthquake record that we're about to use is called Kobe. In the first lecture, I showed you some after effects. Remember that whole freeway that was just like totally on its side? That happened during the Kobe earthquake in Japan. This is a scaled down record of that, and it's going to be the first one that we use to test your structures. So let's see what's going to happen.
All right. You want to hold on to it?
Yeah.
Hold on to it. No.
Oh, we didn't. Oh, yeah, because it might move.
Hold on to it. Wait.
So what happens is when we turn this thing on, this thing centers itself, and I'm afraid that just when we turn it on, it's going to break.
Okay, hold
Should
on
we take the weight off?
We could.
We have enough time.
No.
I really don't want to break it right when
Why? We learned from last time. We broke it before we even started, right?
It was very anticlimactic, and I didn't sleep that night.
Okay, hold on.
That's me every day.
So just that, I was afraid was going to break it.
Oh,
Yeah. Oh, it's
Holy cow, it's so intense. I'm on the edge of my seat. I'm scared. People's lives are at stake. I don't want to sound mean, but I kind of want something to break, like really bad.
Servo and the chicken blows up.
Oh, the teacher.
here it comes.
No, wait. I'll give you the countdown. Don't
She'll
worry.
give you the
So don't start
countdown.
your video until I say 5, 4, 3, 2, 1, something like that. Okay? I'm just
It's going to
starting
be
the
on
software.
Snapchat, Instagram. You guys on Instagram?
This is going to be all over.
It's gonna have like a million hits in like 2 seconds.
Okay, are you guys ready? Yeah. So this is our Kobe earthquake. 5, 4, 3, 2, 1. It's going.
That's what happened.
there you go.
Beautiful.
All that work for 1 second, right guys?
Your structures will not break that quickly.
Hopefully.
Hopefully. All right, so I'm going to pull up the project document, and we have. I'll be right back.
Cool, I usually just do it.
Hey guys, please hand up.
There's a video.
Project.
I'm watching it.
Oh, that's me. Ow. Hold on, that's
Look.
grabbing it by the
Do you guys expect it to fail that quickly, or do you think it's a lot longer?
No.
I was a lot of weight on it.
Yeah.
This is for you.
My hands are in the way.
That's so beautiful the way that failed.
Is it?
Oh, yeah.
Are you gonna post the video?
Yeah, I'll post the slow-mo video, so.
Yes.
No point to save this, right? Not like the other one?
The video. It'll probably work. Just let go. It's ready. Actually, you have the same name as me.
Yes.
You're the same, man. That's look really similar too. He can be your older brother. Max's older brother was found on March 11th, 2016. Dude, no, look at that guy. His name is Max. With my camera. Okay, look at him. He's like you guys are wearing the same thing. He's like your twin. You could be an older twin of yours. Wait, that doesn't work, does it? Okay, no. Okay, never mind.
Thank you, Aaron.
Let's forget about
Thank you
that.
for sharing that story. You were very fascinating.
Okay, that could make sense.
All right. So,
No, they're 25.
so you guys have your project document. You can follow along as I just kind of talk you through details of the project. So you can scroll down for me. All right, this is our timber structures project. Here's our introduction. All right, let me get a volunteer to read the introduction for me. Don't all put your hands up at once. I'll throw a lollipop at you.
Oh,
Can I
lollipop.
get, it's right there in the white shirt. Loud and proud.
Timber or wood is a widely used construction material, especially for residential structures. Wood construction is also common for low to mid-rise commercial buildings, structural walls, and diagonal are used to provide stability and let off force resistance for these structures. Without these systems, timber structures can undergo catastrophic failure during an earthquake as seen in this.
Okay, awesome. And you. So the project is a team competition. You'll be in teams of 3 or 4, right? That might change. I think that's how it was last time.
Yeah. I think we do have a team of 3.
Oh, you guys are already in teams.
We have
From
some
lab
teams. We might have a team of 5. I'll double check on that.
Okay, well, they'll be in teams. Each team is scored according to a performance index, and the highest PI will win. I'll tell you exactly what the PI is. The point is, this is a competition, and there will be a prize. The project and the competition happens in three phases, and we're going to read through all of this right now. So phase 1 is a research and report on some of the characteristics of timber structures and how they perform during earthquakes. Can you scroll down to research, Benjamin?
Great.
So I'm not going to read through all these, but these are this is going to be like a homework type assignment for you guys to do over the next week. Researching timber structures, basic structural concepts, structural design principles. Some things that we didn't get to talk about in our lecture, you guys will research on your own and talk about those. And some of the things we did talk about in the lecture, and you'll just go into a little more detail. You can go back up to the phases. Okay, that's phase 1. Phase 2 is to design your structure and to predict its performance. So, based on your observations of the failure of the basic structure and the results of your research, your team will design and construct a retrofitted structure. The word retrofit just means that it existed already and now we realize it's not going to be strong enough, so we add more structural elements to it, and specifically an LFRS. That's what you guys will do. You'll design it. It's important to note that the structure that was built today, you guys will build that exactly. So it'll be exactly like that, then you will add on things. So everyone will have the same amount of windows. Their structure, they put 2 doors on for fun, but there's actually just going to be 1 door for you guys. So everyone is gonna build that exactly like that, and then after that you can add on. And this phase 1 and 2 will happen within the next week. So when we come back next Friday, you guys will have done your research and you will have come up with a design. You will not have started building yet. Next week, after we check your designs, we'll give everyone materials, and then you'll actually build your structure. Phase 2, part B, is predicting the dynamic behavior of your structure. This begins by thinking of the Lollipop model, and then there's even more specifics from that we're going to talk about next time in a kind of short mini lecture, how to use some properties to predict the dynamic behavior of your structure, like the natural period and frequency, but then using that even more to predict something else. Then finally, the last time we'll come in, we'll test your structure under 3 different earthquake records. So we can go down to the next section and talk about the design specifically. Okay, so this next section just tells you exactly how to make your structure. Again, everybody has to make it the same. There's nice pictures that show you exactly what it looks like, and the dimensions are there too. The structure is 4 inches by 8 inches. It's the footprint, and the height is about 10 inches. We don't have to go through each of these. So you can go down. Basic frame, good. These are all just detailing to help you guys build it. This is what one looks like when it's all done. Okay, now, retrofit. Can someone read this first paragraph that says retrofit? Someone who hasn't. Has anyone not got a lollipop today? I just want to make sure everyone has a lollipop. So I'll probably give you guys a lollipop on your way out anyway. Okay, so someone read this for me. First hand. All right, you in the back.
We observed failure of the basic frame during the demo, so we know that we must improve upon this design. To improve the structure, your team will design a retrofit that includes a lateral force resisting system. Your team will choose to make either a braced frame or a shear wall. Gusset plates at the joints can also be incorporated. Remember that every LFRS must span the entire height of the structure.
Okay, sorry, keep going.
Altogether, this will increase the stability and stiffness of your structure. Refer to the following guidelines in Table 1 to understand the design guidelines.
Okay, so gusset plate is, the way we're going to use a gusset plate is not specifically what a gusset plate actually is, but we didn't define that, so I'll tell you the other thing you guys can use. So there's no moment frame option here. So you guys will either design a brace frame or a shear wall LFRS, but we also have, you guys can buy these little guys. They're little squares. We're calling them gusset plates. In a way, it's actually kind of a way to make it more like a moment frame because we're fixing the joint. Okay, but you guys won't do that for your whole structure. You can buy those to kind of reinforce the joints if you want. Hopefully that explains that. And then there's some rules for each of these things. So for the braces, we'll get there's only one type of material you can use for each of the brace, and it can't fill any doors or windows. Shear wall, there's only one type of material. It's these panels. These guys. That's what you use for your shear wall, just like this one is done. Do you notice something? That this says it has to span the entire height of the structure? Does this span the entire height of the structure?
No.
No. That's not what we want. So you guys will build your LFRS to span the entire height of the structure. Think of that, the rain gutter and the load path, right? We need something going along the whole height to take the force all the way out. These rules are pretty simple. And we'll preset those gusset plates for you if you want to use those. You guys have a cost, a budget, and a limit of the amount of materials that you guys can buy. So they all have different costs associated, and there's a limit. All right. We don't have to go through all this because this isn't going to happen for a couple weeks. And we're actually going to help you, but you can go up a little bit. Actually, I wanted to mention one thing. Yeah, up, down. One, yeah. Okay, so one thing I wanted to mention here is that we'll talk about this more next time, but there's a way that we use the natural frequency and the natural period. We use that to predict how much acceleration the structure is going to see. So we're going to attach an accelerometer. That's a device we use to record acceleration. On the top, we're going to put that on the top of your structure. We're going to record the acceleration, and we're going to check your predictions to what we actually see. But other than that, we're going to be helping you guys as far as setting it up. There will be some data collection that goes on here, but we're not sure. We said, like I say here, this data will be loaded onto a flash drive. We didn't end up doing that last time, and that's still something in the works, whether or not you guys are going to be doing something with your data. Or we might just look at it real quick and check if your prediction was close to what was actually observed. Okay, performance index. This is the key. This is the most important part of the whole project. So, as noted previously, the role of a structural engineer is to ensure a safe design while aiming to reduce costs, right? Remember the muscle guy and the weak guy and the two different weights, and we talked about how if you're going to hire one to do yard work, one of them is going to cost more per hour because he can do more work. We have to think about those things. We think about capacity and demand, and anytime we increase capacity, we're probably also increasing cost. So in order to simulate this reality, the performance index will score each team based on 3 aspects. The structure performance under earthquake motion, the total structure cost, and the total structure weight. And that's done using this equation. So how do you guys think this affects it? In the previous class, there was no exponent on any of these. I've added these in to kind of change a little bit of the way the PI works. What do you guys think this means when you see that? It should tell you something about the importance of each of these factors. Yeah. Yeah.
It should be cheap, but it should also, if it survives all earthquakes, but costs a lot to have a very, someone's not a low, a high performance index.
Yeah, exactly. So the idea is, just because you survive all 3 earthquakes, that doesn't necessarily mean you're going to have the higher performance index than somebody else who also survived 3 but used less cost. This is squared, meaning that it's going to have a greater effect. So the thing that you have to worry about the least is the weight. The weight is a factor of what you put on, but also how much glue you use. But it's still important, and that's, in other words, we want to make sure you guys just don't blob so much glue and put it everywhere, right? But you do have to think about the fact that if you use more glue, you might also make it stronger. But the point is, it's less important. The number of earthquakes is the second most important thing, but the cost is most important. So we really want you guys to spend time looking at the budget. And I gave you some hints, talking about the something about the brace frame. It doesn't have to be in every bay. So how many bays is in this structure? 4, right? If I look at it this way, there's 2 bays. Okay. You don't necessarily have to put a braced frame in every single bay, nor a shear wall in every single bay. Okay. The other thing that you guys can think about is we're only going to shake it in this direction. Okay. So what you do to this side, if you put a brace here, that doesn't have as much of an effect as if you put it here, because it's perpendicular to the way that we're shaking it. So the braces that are parallel have more of an effect. That might not mean that you don't put anything here, but you guys have to think about the most important places where you want to put braces or shear walls or gust plates. That sums it up, and that finishes our time. Yeah.